Joining us once again are Thomas Wire and Gregg Wong, who many of you are already familiar with from our prior interviews. And today we are going to do a deep dive into all things ground testing. Gregg, we'll start with you, brother. How have you been? And can you tell our audience a little bit more about yourself?
Sure. My name is Gregg Wong. I am AEMC's technical training supervisor, and it's my job to run around the country and teach everyone a little bit more about ground resistance testing and how to perform it accurately when it matters. We also teach seminars on insulation resistance testing and other subjects around any of the instruments that AEMC Instruments manufactures.
Kind of like that one that Tom's got right there.
Yeah. Friendly megometer.
And the nefarious Thomas Wire, sir. How you been? And can you refresh our audience to a little bit more about yourself?
Nefarious is a generous name.
Infamous.
Yeah, Micah. It's good to be here again. Tom Wire, Risa Power, senior technical trainer. I like to travel around the country as well and train our guys at various locations on how to do all things that NETA test technicians do.
That is fantastic. And as mentioned in the intro, we are here to discuss ground testing until you're tired of hearing about ground testing. And so with that being said, I'll kind of throw out just a generalized start to the conversation here. So what are some of the concepts for why we even have ground testing? And I'll turn the floor over to you guys on that one.
Yeah, so, this question comes up quite a bit is why do I have to do this measurement? And we see it done in various phases that we're all somewhat familiar with. We have the acceptance testing or proof testing. I've just installed this. It's just been built and I need to verify its resistance to ground, whatever it may be, some electrode system. And then there's, of course, other testing that may fall into the category of ground resistance testing. And then there's maintenance testing. And I think a mistake that is oftentimes made by individuals, even inside the electrical testing industry and definitely outside of it, is that we pound this ground electrode into the ground and we don't see it anymore. And so if we can't see it anymore, everything's fine, right? It's working. And this is not some system that is oftentimes, hopefully not utilized very often. So we don't necessarily see any type of performance issues that are related to the ground electrode and its resistance to ground. So why is it that we have to perform this? Well, let's remember, first and foremost, we're pounding a metallic object into the ground. When we do that, we may cause some type of damage to its copper coating, right? Usually electrodes are copper clad. And when we pound this thing into the ground, it gets scratched up by nearby rock and other types of materials that are hard on it. It then begins to corrode and it will corrode maybe exceedingly faster than it would have otherwise. So we are introducing this object into the ground. It's going to experience some type of stress. And that stress can cause it to fail, whether it be prematurely or otherwise. Let's also remember, too, ground electrodes have a lifespan. And depending on where you're located, that lifespan is going to be dramatically different. If I drive a ground rod here, where I'm at in North Texas, that is galvanized, for instance, it doesn't have a very long shelf life in the ground, or I should say shelf life, service life. Versus a ground electrode that may be pounded in a completely different part of the world, it is going to perform much, much different. It's going to last longer. We have very low resistivity soil here in North Texas, so we have a lot of issues with galvanic corrosion. So these systems, they can fail. And humans, of course, can cause these to fail too. Everybody's got the same story of the guy with the excavator or the landscaper that tears up a ground electrode or a ground electrode bond, or ground electrode conductor. So these things are not just installed, set it and forget it type devices or objects. We have to continually test them to validate that they are of a sufficiently low resistance to earth to make sure that they are going to work when that time comes.
To add on to that, I would like to say from the NETA perspective, right? Most what is the real intent of your ground grid, of your grounding system, right? The real intent of your grounding system is not to save your life. The real intent of a grounding system is to provide an alternative non-current carrying conductor under normal conditions. It's a non-current carrying conductor, not your neutral. It's just a grounding, unshielded, bare might be quite often, conductor that allows fault current to return back to the source. That's what we're doing. And in the process of having that fault occur, that current is flowing through that conductor, and all conductors have a known resistance per footage, and so they have a resistance to them. And so as that fault current of 1200 amps flows through this, this copper wire or whatever you might have, 4-aught, it's going to generate a voltage. And that's your other problem, right? So the first problem that you're going to have is that you're going to have to get that current from the fault location back to the source. The second, that way you're not just sitting there humming some source, some load out there at fault voltage. And then the other reason for it is your ground grid testing. You want to check the grid and make sure that you have a low resistance to earth, because if it's going to build a voltage across those conductors, you want your grid to be at the same voltage as the earth you're standing on, so that way you are not at a different voltage and it shocks you too. So both of those are preventative measures to help facilitate the safety aspect of it. But ultimately, it comes down to trying to make sure that we can identify the faults. And the tests that we use are there to ensure the integrity of that grid, the fact that it has good continuity, and the fact that the grid itself is bonded to earth sufficiently enough for the fault current that it's installed at.
Yeah. I think it's worth mentioning as well, too, what the purpose of grounding is, which you nailed the big one there, right? Which is going to be limiting. If we go to NEC 250 and look at exactly what grounding is done for, you'll see the word limit and stabilize show up. And those are two separate subjects, but limiting those voltages during non-normal operation is the primary function, in my opinion, of grounding. Now, there are a lot of other functions out there, and it depends on what the kind of the system is, of course. We want to minimize common mode voltages, all sorts of other functions for grounding, but generally speaking, it is to limit and stabilize, limit our voltage during non-normal operations, stabilize during our normal operations. And it's critical, and this makes a lot of sense when you get into what the earth electrode connection is, but it's critical to understand that ground resistance is incredibly variable, not only location, but also time periods. So if we go through a wet season, of course, we know that we would think, at least I should say, that we expect it to be a lower resistance time for our ground electrode. We expect the resistance of that electrode to be lower. Generally speaking, that is true. However, I have learned through working with our customers and being in all sorts of parts of the world, that's not necessarily always the case. So there are extenuating circumstances here. One of the recommendations I always give to individuals that are responsible for putting testing plans together is non-annual testing. Don't test every February. Stagger your testing because the atmospheric conditions are changing. Secondly, as we move into different locations, the geology changes. Again, an example from here in North Texas, I have a very low resistivity soil, but if I drive just 45 minutes north, that soil starts to turn into oxidized iron, and I get that red clay we start to run into. It's this silty material, clay material that incurs a much higher resistance. And it's not that we did the test wrong. We just are testing a completely different substance. The earth is literally changing. So we have to validate that our design meets our specification. And that's really, I think, where we get into what is a good and bad value. And I don't like to engage in that conversation. We're going to refer to our specifications and our standards for those directions, right? Everyone thinks the NEC says 25 ohms. That's not the case, right? The NEC doesn't have a specification. It says 2 electrodes. 1 electrode can have 25 ohms. 2 can have any resistance you want to. That's why we don't see ground resistance testing done very often in just general purpose installed electrical systems. But, to really answer the question, what is the purpose of ground resistance testing? We want to validate that our design meets our specification. We want to maintenance test to make sure that we are still meeting our specification. Why we do these things, why we have these specifications, limiting voltage, stabilizing for operation.
Now, what are some of the guiding documents out there and standards that are out there that kind of address the topic?
Yeah, go ahead, Tom.
I would say the ones from a testing perspective, any NETA technician or even the sales guys, one thing you're typically always going to see your customers reference is IEEE 81. That is really probably the gold mine for all requirements to meet. The next one after that is probably going to be IEEE 80. Gregg and I were talking earlier, the Green Book, the old Green Book, they're planning on remaking some of these. It is IEEE standard 142. I will say that I think all of these are now currently greater than 10 years old. So technically they are all outdated standards according to IEEE, and they should be coming under review shortly. I think some of them already are. Yeah. But so keep an eye out for those. Some other really good ones that I think that are worth highlighting is one is Getting Down to Earth by Megger, really good, valuable resource for test technicians and helping you to understand that stuff without having to download IEEE 81. And then, Gregg, you can go ahead and talk about the AEMC one as well.
Yep. Yeah, I'll mention a few others as well, too. So AEMC has the Understanding Ground Resistance Testing Workbook. You can always reach out to us to receive a copy of that. It's a wonderful resource. It's a field guide. It also has some blank test reports in there as well, too. If you need examples, you can download those examples also from our website at aemc.com. We have the workbook as well as Excel templates and printable documents that you can take out in the field for your testing. It'll give you both instruction as well as a report if you need one. I'll mention some kind of niche ones, documents that are worth referencing, even if you're not in these industries, because they are so valuable and fairly easy to access. Military 419A is the document behind a lot of the IEEE stuff. And you'll find some disagreement in some of them. We'll kind of skip over that. It's kind of really nuanced. But if you need a great explanation into the theory of ground resistance testing, or really just the theory of grounding, the 419A is a fantastic document for that. It's very wordy. It's tough to read.
Is that an IEEE standard or
that is a military standard?
Okay, the 419 mil spec.
Yeah, it's a mil spec. Yep. The other one, it comes from Motorola, and that's the R56. And again, that may be a document that you're saying, oh, that's not really applicable for me. The testing portion of it, which is a small portion of it, but probably 50 or so pages, is very, very well written and generally available out there if you Google search it. I believe they've made that public. I'm not exactly sure. But it's a wonderful resource nonetheless, if you come across it, for understanding these tests. What they've done very well in this is present alternative scenarios. You cannot perform this method. Here is an additional or an alternative method for testing as well. So great resource, not only just for ground resistance electrode testing. I prefer the terminology resistance to ground. When we're performing like follow potential, I think that's a better generic term for it. We say ground resistance testing, that means a lot of stuff. But if you need soil resistivity or ground resistance, resistance to ground testing, and then how to come to some conclusions, do some basic calculations to approximate resistance, is a fantastic document for that one as well too.
And that's a great segue as well into kind of like talking to the actual testing. So we talked about the concepts of it. What are some of the tools that you guys employ out in the field that help you determine your results?
Yes. So when we do resistance to ground testing or soil resistivity testing, we're going to generally rely on an instrument that is has some certain number of terminals on it, also referred to as poles. The follow potential test is the kind of gold standard for resistance to ground of an electrode system, whether that be a single driven 10-foot ground rod or a 400 by 400 substation. Now there are alternative tests that are similar to follow potential for scenarios like that. That is one of the, probably the question that we answer the most here at AEMC Instruments is I have this giant thing I need to test. It has 50 ground electrodes. I can't do a follow potential because it would require me to go super, super far, right? There are alternatives there. In the document that Tom mentioned, the IEEE standards that he mentioned reference those as well too. So we need some type of instrument to do this type of test. We need it to have some type of terminals. We refer to these as poles. 3-pole instruments going to perform our generalized follow potential test. 4-pole instruments allow us to do soil resistivity. However, it's worth mentioning at this point, a 4-pole ground test instrument is a wonderful follow potential measurement or resistance to ground measurement device when we're talking about something with very low resistances. The reason for that is consider that everything you connect to your instrument also incurs a resistance, especially when we refer to that connection to the electrode itself. So if I have my electrode, I have one lead coming off that electrode to my instrument. This lead has a resistance, and this lead is now a series resistor in that measurement. With a 4-pole instrument for resistance to ground, I can then eliminate that lead resistance by placing another lead in place there in the same location that my E lead or my green lead is placed. It's connected to my electrode, eliminating that lead resistance by taking a voltage measurement. So one of those, it's a quick trick here to ensure accuracy and to better perform the measurement is a 4-pole instrument is a lot more flexible than just a standard 3-pole. And most instruments out there, whether it's from AEMC or others, are 4-pole instruments.
Okay, I was kind of
they're often just not utilized to their maximum potential.
What are some of the reasons you think are for that? Is it just a lack of knowledge?
Lack of knowledge. Yeah, read the manual, man.
RTFM every time, Tom.
Yeah.
RTFM, man.
That book.
To add on to that, Greg, I would say, and I'm going to give you a little bit of personal Tom talk right here, is if you ever see, like, I'm not picking on Megger. Look, if you could sell them, I understand that too. But Megger has like a DET 3/2. It's a 3-terminal test set, and you can get a 4-terminal test set for just I think about 10% more in cost. And so the cost increase versus the versatility that you get back out of it, it's absolutely a waste of your money, in my opinion, to spend it on a 3-pole test set. Just go get the 4-terminal one and have 5 more tests available to perform in your toolkit, right? Yep. Versus being limited only with, your 3-point tests. So the other thing I want to kind of highlight real quick, and Greg, I don't know if you have like a 4-pole terminal test set there, but if you look at those, that beauty right there. If you look at those terminals on the left right there, and some of you guys might be able to see it, at your own shops or whatnot, but every test set manufacturer calls them different terminals, ES or X or C. I'm not going to dive into what the difference is between all of them. There's usually 3 different formats of what they name their terminals. Fluke, Megger, and then I think there's one more. And anyways, if you just compare them directly to this guy right here, a 4-point ground test set is exactly like a DLRO with 2 potentials and 2 currents, except for it runs at 1,000 hertz AC or whatever frequency, right? That's the only thing. And it runs at milliamps. It's the exact same test set for the most point. When you do a follow potential, you just bond these 2 and you run it directly to your ground probe. You take this, your C lead goes out to your far probe, and your P lead goes out to your moving probe. And so it's the exact same test set. It's just that you need to perform it as AC in order to get an impedance measurement off of it.
Yeah, so to build on that as well too, that's exactly right. If I look at a 4-pole test instrument, and we go over this in the seminar, this is a multifunction instrument. It's going to perform soil resistivity testing, follow potential, both in 3 and 4-pole setups. This one can even test a transmission tower with our ground flex fuel kit. But end of the day, outer 2 are going to be current terminals, right? inner two are going to be taking some type of voltage measurement. We have current flowing. We're creating a circuit. A voltage is then applied because there's a resistance in between here. A current begins to flow, and that current is then measured along the traverse between these two terminals. And it doesn't matter if it's soil resistivity testing, fall of potential, the measurement is generally the same. To complement what you just said, because it's a wonderful observation, I've tried it. I've taken AEMC's version of the DLRO, the 6240, and I've done some just kind of shallow soil resistivity testing just to see if it's working. I'm not going to imply that you actually go out and do that. And the results are very, very similar. The difference, as you identified, though, one of the principal differences outside of those instruments, the DLRO not designed for that purpose, is going to be the fact that I'm testing at usually 128 hertz with an instrument like this as a square wave versus just a pure DC measurement. Those of you that are more familiar with soil resistivity testing specifically, you may be familiar with other more advanced instruments out there. The Mini Sting comes to mind, Super Sting, or the Iris as well too. Those are DC direct instruments that are looking for the decay of that DC current that was applied. It's a different test procedure, but very similar to a DLRO in that respect. A lot more test current being applied there. But the test instrument itself remains largely the same. We're using the same principles that we see show up in other test instruments, like for other resistance testing instruments, I should say there. The test instruments are going to be specific to the job. If you're looking for something that is going to cover all your bases, a 4-pole instrument is going to be the best. I think it's also helpful for us to define that what is under that ground resistance testing banner here too, because I mentioned a multifunction ground test instrument. 3 tests really come to mind here, and I'll give a shout out to a fourth as well too. Resistance to ground testing. This is going to be, I have an electrode or an electrode system, being a bunch of electrodes that are interconnected and show up as parallel to the earth. This is going to be that fall of potential test, but fall of potential is one method for resistance to ground testing. There are other methods out there that are more applicable in specific scenarios. Outside of that are soil resistivity testing. If I were going to put these in a more logical order, I would put soil testing first. This is going to allow me to perform a measurement of soil resistivity or resistance. We turn resistance into resistivity for then designing a system or even maybe troubleshooting what measurement I'm receiving on a resistance to ground measurement. This can be performed usually a number of different ways, but most of the time we're subscribing to the winner test procedure, which is a 4-pole test method for soil resistivity testing. It's simpler, easier to perform, but there are other methods out there, of course. The last test procedure, or the second to last, is not a resistance to ground or even a soil measurement at all. This is going to be those, point to point, or equipotential, or also could be called continuity measurements. We're testing here a bonded system, right? For those of you that have done this in a substation, this can be, 1,000 measurements or more in some cases, where I'm moving just throughout the substation, testing individual components of the bonded system and measuring their resistance. I want to see that obviously be very low, so that everything is interconnected well. The last measurement I'll mention that can fall underneath this category, very similar to the resistance to ground measurement, is going to be like step and touch potential measurements. Now, these are largely more or less calculated anymore. However, we can perform these measurements with a 4-pole ground resistance test instrument, or other testing procedures now exist to validate that our design meets our specification.
Any thoughts on that there, Tom?
I think that pretty much sums all of them up. I would like to say that the 4-point test set that you have can perform the soil resistivity. That's the quality of your soil. That determines what kind of conductors you need to put in the earth, right? And how you need to bond those conductors to your earthing system. And so that 4-point test set will perform that test, and then the 4-point test set or the 3-point. Why get the 3-point? Just get the 4. And that will perform your follow potential. Your point-to-point can be done with your 4-point test set. Commonly, people do that by bonding your voltages and currents together, and then they just have to measure your lead resistance. I'm going to give you a little tech tip right here. I personally don't like that method because that's a coiled up bundle of wire and you're performing an impedance test. And as you string out more wire, what do? You just change that coil's inductance and you just change the entire measurement of your resistance. And so you measure that wire. What are you going to measure it with? You're either going to jumper it together at the test set and just press start. Oh, I got 1.4. Okay, write it down. I'm going to subtract 1.4 from everything. You spool that coil out, and what do you get? It's not 1.4 anymore. It's 1.8 because you just changed your inductance. So I personally will I might take like my test set and set it right next to the probe that I'm testing at 1, and I'm going to point to point to another one, right? And so I have a really short lead here. Who cares about a short lead on a point to point, right? We care about the 100-foot leads. Those are the ones that really have a value that makes a difference. So then I'll run 200-foot leads out, and that'll be a separate voltage and a separate current, just like you do with your DLRO. Right? And so that's how I'll typically run that. But the fall potential and the point-to-point and the resistivity can all be done with a 4-point test set. You can also do the point-to-points with a DLRO or a 100-amp inductor or whatever you need to do. Quite often it's done, customers might require a 100-amp or a 300-amp inductor just because they want to verify ground grid integrity. They want to check the joints during the fault current. So that might be a part of your requirement. And then your step in touch is usually going to have to be done while the system is off, unless you have an off frequency injection. And so, because otherwise you'll just measure noise during the whole time. So you got to make sure your power grid or your substation's off, and then you can measure your step in touch by doing a current injection or some kind of method along those lines. Right. In all honesty, if you're checking your grid and you can honestly go ahead and probe throughout your substation with a follow potential and just make sure that you have a good earth nearby. Most of the time, step in touch is usually not too much of a problem. And I don't know. There's other meters out there that could probably do that a little bit better than a 4-point test set.
100% agree with that.
The last thing I'll say is that quite often I've been starting to see these getting used a lot more for probes, whether it's the ground grid itself or just an individual rod. Understanding these tests, and we'll pop up a little thing showing this, is you have to understand that this only tests a loop. And there's so many different flavors. Gregg has a different version of this, different manufacturer. But the thing is that the way these things work is you have 2 clamps inside of here, and one clamp injects a voltage, and then the other clamp measures the current that flows. And so it knows voltage divided by current. It can do its own math, and it can tell you, oh, well, I have a resistance of this. It's AC because it's induced voltage, so it has to be AC. So it means it's an impedance measurement. But this requires a loop in order to work. You can't just go up to one ground rod, clamp that thing on there and check it, right? That's failure mode all day long. The other thing about these is any test set that you ever have in the history of never ever, I've always recommended to go ahead and get the damn little thing out that says a calibration check. You put it in there. Yep, it says it's 5 ohms. You take it off. Oh, it says it's infinite. That means it's working right. So with the AEMCs or the 4-point testers, you can short all your leads together. You should get a 0 ohm reading. There's different ways of doing your functions check, but I always recommend get the low-hanging fruit out of the way, because if you run into an issue when you're testing, the last thing you want to do is just be like, oh, man, it's just a bad lead. I never checked it. It'd take you 40 minutes to find that problem. So just do a quick function check before you start.
To build on this guy, because this is, if there was a controversial subject in ground resistance testing, this is it. And I've sat and many service managers' offices who are much more intelligent than I was, and they absolutely despise this thing because they had a bad time with it one time. And I think it helps to break down exactly how this works. And Tom's exactly right. There's two heads inside of here. They're electrically isolated from each other. One is inducing a voltage, which allows a current to flow. And the measurement is assuming that this voltage remains the same. It's constant. So we have a current that is returning. And how I always simplify this is to go back to that old adage, which we know is not exactly true, of charge is going to travel towards the path of least resistance, right? If we're attached to a grounding system that is bonded, let's say, to the utility, easy enough to picture that, right? We have a ground electrode conductor that's going up, that's making a neutral bond. That neutral is going out to the rest of the world, essentially. And there is a effective, solidly grounded system behind it that is, for all intents and purposes, infinitely sized and essentially 0 ohms. It's not 0 ohms, but it is essentially 0 ohms. So that's the way my current's going. My current's going out there, and it's finding all these parallel paths through the utility system to come back through my electrode system that I'm testing. Right now, it's a little bit more complex than that. As Tom mentioned, this is an AC. It's off frequency. Usually they're injecting somewhere in the range of greater than 1,000 hertz, usually 1,500, or like this one, for example is at 2,000 hertz, or it's 2,078 hertz exactly. So as this test current flows out, it finds all these parallel paths, it returns back into the instrument. I now have a voltage, I have a current, I have a resistance. We can break these down even further now. This one has an advanced mode. I can see what the inductive component is doing. Because I'm working at such a high frequency, I can do other stuff with this instrument. I can produce different values. Generally speaking, we see that resistance and our impedance are equal to each other. But now you can see some additional factors with your instrument because we see additional technology being built into these instruments that give you additional functionality. I think what's really neat about this one, and not a lot of people realize this will do touch voltage as well too. So when I clamp this on, I can actually get a warning if I'm greater than 50 volts. However, in the advanced mode, I can measure a voltage just by simply clamping it on to that ground electrode system. But it's critical to understand this is a loop impedance analyzer. We call it a ground resistance test instrument because that's what everybody thinks it is, right? It for all intents and purposes, it is. But it is a loop impedance analyzer and can be utilized as such. For instance, in the lightning protection industry, this is often used where point-to-point continuity measurements cannot be effectively performed. For instance, where a roof penetration is for a ground for the lightning protection system on top of a high rise, for instance, I can't effectively measure that when everything is self-contained, but hidden, concealed within the building. I can now measure that because I expect to see that test signal looping through the system and returning back to the instrument. So a lot of flexibility in these instruments. Downside to this thing is that we're always taking it on faith a little bit. With fault potential, I'm taking multiple measurements. So if we're using this and we need to validate our measurement, let's look for additional electrodes that can be measured, and we should see some similar resistances. That's really where I think this instrument can be misunderstood, is that depending on where I'm clamping it is what I'm going to measure. For instance, if I have two ground rods that are next to each other, one's here and one's here, and I clamp below this bond that's interconnecting those electrodes, I'm measuring this electrode and this electrode, right? I get the individual resistances. However, in this example, if they're very close together, if I do just a simple parallel resistance calculation, that is not going to be the resistance of this system. These electrodes are too close. So be aware of what this instrument is and what it isn't. And this is why we see this instrument that is specifically not specified, or it is told in the specifications we cannot use this instrument, because it's oftentimes misunderstood. It is incredibly similar in its measurement capacity that a fault potential measurement is. Easier to deploy too, of course. It's just been kind of bastardized, unfortunately, in the industry because somebody had a bad experience with it one time and didn't understand it.
Take that and run with it. So I wasn't going to go down this path, but since Gregg already started there, he opened up the doorway and kicked me right through it. So I'm going to give you two scenarios. One is this is why you shouldn't use this meter. And I'm going to give you a scenario that is why you should use this meter. Yep. Okay. So the first scenario, and I'm not picking on people. Some people, they do things and they don't always know. So in my past, when I was in the Army, we used this at one time when we had generators. And what the established doctrine was to go ahead and put a ground rod on each side of the generator and bond that ground rod to that generator. And yeah, we're going to have a couple other generators in parallel, but then you're going to go up to each of the ground rods and you're going to put this side on there. You're going to clamp it. You're going to say, hey, it's less than 15. Cool. Move on. Next one, they should all be less than 15. Well, guess what? Every single one on each generator, for both of them were the same number. Well, why? Mm-hmm. Because exactly what Gregg just said. This is a loop check. Yep. So it's injecting through the earth down, comes out the other ground rod, comes back up to this ground rod. It's only checking itself. The only way that this really works well is when I have like 18 ground rods, right? Mm-hmm. And so then it goes down one ground rod, it goes through the earth and comes back through all 18 as a parallel path. And then all of them, because they're in parallel, they basically reduce down to a parallel resistance, which is very low. And, that they all might be 15 each, but 18 or 15 divided by 18 is less than 1. So now we got 15 ohms on this one rod plus the 0.6 ohms. Well, now you're actually getting something more comparable to what the ground rod really is. So they were just doing two rods, and that's the wrong scenario for it. So that's why I personally, every time someone pulls one of these bad boys out, I cringe. I cringe so bad because it gives me horror stories from when I was in the Army. So that's now the second one is great use for it, right? So utilities like to use these commonly, and they'll go up to a telephone pole and they'll have a grounding rod come down or conductor, and they'll go ahead and that goes up to their shield wire at the top, right? Mm-hmm. Bonds to their shield wire or neutral. They'll go up and they'll measure the one rod. The thing is it goes in the earth and it comes back up 100 other rods back up to those shields, like I was saying before. And now we're only really checking one rod. All the rest of them have an infinite parallel path. And so at that point, perfectly acceptable, right? So you have to, it's like any test, right? If I use a multimeter and I want to go measure how much current's coming out of my battery, I'm not going to set this to amps and go right across positive and negative, right? You have to know how to use the test before you employ it.
Mm-hmm. Yep. Yeah. And that's probably the chief issue that we hear about this instrument. When we look at our tech support calls, it's usually how do I apply it, or I'm producing this value. What does this mean? Your ground electrodes don't have, most likely, a quarter of an ohm of resistance to ground. Most likely. I mean, there are scenarios that will be the case, of course, where we have, like Tom mentioned, we have 18 ground electrodes in the ground, or we have a very, very low resistivity soil. However, generally speaking, I can safely assume that I don't have a quarter of an ohm resistance on a single electrode. We hear though, hey, I got this measurement. This instrument in particular will produce a loop alarm, and that is not a magic loop detection. It's simply saying you have a resistance threshold of 5 ohms or less. You've met that threshold. You could potentially be connected to a loop. For instance, in a cabinet that has a bare ground electrode conductor that is somehow making contact with that cabinet in two locations, has developed a loop now, and I've clamped onto it, and I'm just seeing that test current return over and over and over again. We're going to consider how the instrument works, and then we can apply it correctly. I think the best way to simplify it is to remember that it's a loop impedance analyzer, and think about the path of least resistance, where that's going to be. That's where your test current is originating. It's where it's headed, and it's returning back through the earth if it's a resistance to ground test. You are incurring a very low resistance connection through the utility's neutral, because it is essentially, for all intents and purposes, infinite. And so therefore we are measuring that test current return into our ground electrode. 2 reasons this instrument's going to produce a slightly different value than our follow potential. The first one is the fact that we do have some resistances incurred behind the electrode that is being measured, right? As Tom mentioned, 0.6 ohms, for instance. So if my fall potential measurement was 12 ohms and this was 12.6 ohms, well, that 12.6 ohm is incurred because of the utility system. Secondly, frequency. We all remember way back in school that impedance is a function of frequency, and as its frequency increases, therefore so can impedance. So we've got ground systems are very complex. They have capacitive and inductive components on them. Oftentimes, usually for our purposes, we can somewhat move those to the side. However, in this case, because I'm increasing the frequency that I test at, here I'm testing at usually 128 hertz. Here I'm testing at 2078 hertz. I expect to have some type of inductive property, perhaps, that is going to change the measurement, the impedance measurement on this instrument. So there's two reasons that we could see this instrument be slightly different. However, all things considered, I've done this many, many times to demonstrate this and do training on it. I should see very, very similar measurements on these methods when done correctly. We should mention that fall potential requires isolation, because if I have that looping condition there, I now have a bunch of parallel pathways for that test current to return back into the instrument. I'm going to see a very, very low resistance measurement that is not a true measurement of the ground electrode I'm connecting to. So for fall of potential, now there are ways to move around this that we could talk about, but for a fall of potential where I do not have a current clamp or other type of test method to apply to it, I have to isolate, which means I should be de-energizing in most cases.
Makes sense to me. Now we're kind of on this, and we've talked about various test methods that we can use for various things. Are there any tips and tricks that kind of help expedite this for anybody? And you know, we all met at Power Test, and that was one of the things that you two did, which we're changing out tips and tricks on various pieces of test equipment. And so, are there any good ones that will help folks out in the field with this? There you go.
I got one. Greg, can you pull up that 4-point tester that you got right there?
Yep.
Hey, everyone, look in the lid.
Yeah.
Diagram of how to
exactly.
use it.
There's a diagram. And this diagram covers the majority of your uses too. Doesn't cover everyone, but it covers pretty much everything you're going to do.
I'm gonna go old school dad on some people and be like, you know what? Like when you went to take your driver's test, what'd you have to do? You had to read the manual, right? Most people did. They had to read the manual, so it doesn't hurt to sit there and read the manual a little bit. Another real quick tip I'll say, because Greg had mentioned it about the frequency and being isolated, is that most of these test sets have like a light, or like this one right here will flash up like a dash 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 when it's got like some kind of an error. Usually that is, it's some kind of interference with the test set. So it recognizes that there's other signals present, and it's like, I can't make a proper measurement for you. Mm-hmm. And so quite often, along with reading those manuals, understanding what that means, if you see that little light coming on saying interference and you write the number down anyways, that is you as a test technician just not knowing how to do your job.
Yep.
What are some of the things that cause the interference there?
So exactly what Greg said earlier, right? It could be what if you're doing step and touch potential, sure, and your grid's still on, like your substation's still running. Like, I mean, you have 60 hertz all around you, and you're trying to do step and touch potential at 60 hertz. So some test sets will run off frequency at 59 or 65, or mine's like 1080 here, and his is 2000. Like they'll run off frequency, but they might still get some kind of transient switching spikes or any other kind of interference that might be in the area. If you're at processing plants and it's an indoor sub and you're trying to check the grounding system there or something like that, there's a lot of stray signals that go on. So just
motor what would be like in a manufacturing scenario? What are some of the things that you would see that would cause that? Are you getting like, it's just improper bonding, or are you seeing the transients on the test equipment? Okay.
Yeah, a lot of stuff like that. Anything that really chops up your signal, that can have an effect on. But the thing is like, if you, like Greg said, if you isolate, you should never have that problem. You do a proper isolation, and you know what your test setup is, and you try to make sure that it's set up for that. This should be like a one-off scenario that you run into once in a while, and then that light comes on or the dash 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 comes up. That's a notification to the operator saying, "Hey, double check your stuff."
That's
right?
what I was going to ask. That's
Down.
definitely a leading edge indicator that, hey, you didn't properly isolate what you need to, and
it's
time to go revisit type thing.
I mean, these manufacturers know that there are limitations to their test sets, so they try to help people in identifying those limitations. And if you just don't use the tools to their their maximum extent, then you're doing yourself a disservice at the same time.
And I know that one of the things that we kind of harped on in several of our prior conversations, Tom, this one's geared towards you, is like pre-operability checks and making sure. Are there calibratory methods that come into zeroizing and all that other good stuff with the various?
So there are, like, Greg, you can go ahead and power your one up, and I'm going to turn this one on right now. But like I've shown videos in the past on your multimeter. Like you take it, you short your leads together, you grab something else, you measure your lead resistance or a megger. You short it, you open it, you make sure that you get a known reading, right? So this one right here, it's got a light up screen. It's really hard to see that, isn't it?
It'd be rough. You're gonna have to tell us.
Gonna happen. So it says OL right now. I don't know if I can make that dark or not.
I can on mine.
No, that's nice. Greg's got the new and improved one. So mine says OL right now, so it's basically open line. And then if I go ahead and I put this on here, now it's going to say, and you probably won't be able to read it. It's going to say 5.1, and if you read this right here, it says on it 5.1 ohms. So this is a plus or minus 0.1. So it's a calibration check. Another thing you can do is you can just take a multimeter lead, and I'm going to do this if I can right now with this multimeter, and you put it through and you just short it to itself, right? And then what's your expected resistance of a shorted wire? Zero.
Pretty
right?
close,
So,
yeah.
Yeah, so that's a very easy check that you can go ahead and just put it through, and maybe I can get this to work and maybe I can't. And 0.046. So it's a very easy check that if you just understand your equipment a little bit, what if I put a shorted jumper in there? Yeah, it's a 0. Yeah, that makes sense. It's just acting like a multimeter at the end of the day, right? So just treat it like one.
Yeah, your calibration loop is not much different. It's just got a resistor in between it.
Yeah.
That's all it is.
That's all it is. Yeah, I mean, you can build that. There's nothing fancy about that at all. You could make one yourself with any resistor.
As long as you knew what the base was for the resistance.
Right. Now, one thing to remember with clamp-on test instruments is that they're really good at measuring very low resistances, because what is low resistance when we throw Ohm's law at it? There's a decent amount of current there, right? So there's a decent amount of test current. As we go higher in resistance, now the instrument, because this is a current measuring device, and high resistance here, let's say, is going to be greater than 1,000 ohms. The instrument begins to range different, and we'll see the instrument range 5, 10, 50, and 100 ohms. Now it becomes less accurate. So I wouldn't take a 25 kilo ohm resistor and put it in between a piece of wire and say, hey, this thing works great. Take a 5 ohm or a 25 ohm or a 100 ohm resistor.
To that point, that goes right back into knowing your test set, right? Every ground test set you run into, what values are you looking for? Most of the time, you're looking for a number 25 ohms or less, right? I mean, it doesn't matter what you're testing. Now, if you're testing a single rod out of a big grid, you might get a 200 ohm rod or something like that. And then the old Biddles, you'd have to scale it down or whatever you're doing, right? So, but I mean, know what you're doing, know what you're testing. Don't, like you said, don't get a 25,000 ohm resistor. If anything, get a 100 ohm resistor and see if it measures it right. And at the end, you're not trying to perform calibration. Understand that. You're just trying to make sure that it performs properly. Let the calibration guy do his job, and then you do yours.
You mentioned function testing. I'll mention that, and I'm pretty sure every manufacturer has a version of this for their test instruments. And depending on the instrument too, there may be a different version of this. Like for us, for instance, for instruments that like the 6472 I have, these have internal bananas. So, or recessed bananas, I should say. This is a different calibration checker. We call it a calibration checker, but to your point, I call it a function check. Because it's not a calibration process. This has got a switch on it, and this will allow me just to change the resistance that the instrument's going to measure. I plug this in, it's color coded, I hit the test button, I should see the resistance that's on the box, or a number very, very close to it. If I see a number that's completely different, I'll obviously want to check this first, make sure this is working properly, the checker, and then I may have an issue with the instrument. I may need to set this aside until it's corrected, right? And rely on something that is working correctly. But function checks are critical. This is ideal, but this is not the only way to do it. To Tom's point, this can also be checked with a resistor and some leads. It's not super complex to visualize how this test instrument works, and then to perform some type of function check on it. So you asked, what are some tips and tricks? I think the first tip that you could walk away from out of this conversation is to remember that the Earth is better described as a semiconductor than it is a conductor or an insulator, right? Because we tend to lump things into those groups. Now, I'm not talking like it's the same semiconductor that's in your phone, right? Because that's been highly processed and purified to be exactly, germanium, for instance, or some other type of semiconductive material. Here, we're talking about a mixture of either somewhat conductive, not conductive, or semiconductive materials that exist all layered together, right? We refer to it as the strata of the soil, but it's all very intermixed. And we've all seen this when we drive past a site that's been excavated. Remember that it's changing. It's going to change based on the temperature and the moisture content and all the other atmospheric conditions that will affect the soil. But as an average, the soil is about 1 billion times more resistive than copper. So you're dealing with a volume issue. I take a ground electrode and bond a copper conductor together to it, right? Generally speaking, very, very low resistance. Micro ohms should be, right? I stick this into the ground. Now I'm putting it into a material that be more like bonding it to a piece of wood or some other type. That may be a piece of wet wood, or I'm struggling to think of a material that is a better descriptor there. But it's not very conductive. So I have to have a lot of soil for it to do that same job as that conductor that's bonded to my ground electrode. Another way to kind of think about this for those of you that have gone through electrical training is when we use aluminum and aluminum conductors and bond those to copper conductors, we derate the copper, right? The copper is a better conductor than the aluminum. The ground is a very, very poor semiconductive material, and as I stick a ground electrode into it, I can expect that it's not going to be as conductive. Therefore, I need more soil. This explains partly why I need so much distance to perform follow potential, right? Think of the shells or the amount of soil around the ground electrode as a series of resistors, right? The nearby soil has the highest impact because it's in intimate contact with the ground electrode. As I move further and further away, I see less and less resistance incurred. You can, if you've seen like a heat map for step and touch potential, it's exactly the same. It's the exact same principle that we're applying here for ground resistance testing. Why do I need to go so far away? I need to be outside of these shells, or as far away as possible. Now, outside of these shells, even for a single ground electrode, is pretty far away. It's further than we actually do the testing. It's 200 feet or so. We need this spacing. We need this amount of space so we can find that equipotential or zero resistance connection where I'm no longer incurring a resistance. What is another principle about the Earth that is unique? It's infinite, essentially. It's a giant ball of dirt that we're standing on top of. Because it's so large, but it is so poorly conductive, I can place a remote Earth probe very, very far away and still be connected to the same thing, right? So I think one thing we struggle with when we look at how follow potential is performed is we think in physical terms, right? We don't think electrically necessarily. We think of the geometry of the test and being exactly 100 feet away from a 10-foot driven electrode. Think more in the electrical principles of what you're working in. You're working with these shells that are essentially representative of a series of resistors, right? the further away I am, the more material I have introduced into the testing field between my two electrodes, the less resistance will be incurred the further it is I am away. I need to establish this remote earth probe, the red lead or H, depending on the test instruments, usually always red, is going to be placed so far away that I am in an area that is close to zero resistance, right? It doesn't always have to be exactly zero resistance, but it's very, very close. Other tips here are understanding how your instrument works. I think that's a fantastic one that Tom mentioned. Call the manufacturer. We have a ton of experience in talking to you and understanding what your use is, what your specific application is, and then suggesting to you the right instrument. Yes, we're a sales organization. No, we're not going to oversell you. I'm always going to give you a few examples of why I think this instrument could be better than that instrument, depending on your application, right? Tom and I were
3-pole to 4-pole, just like we talked about. Right?
3-pole to 4-pole, but even model to model, right? We have multiple 4-pole instruments, and there are some that are going to be better for your applications than others, depending on what it is you're testing, right? So the first question we're always going to ask is, what are you performing the test on? What measurement are you doing, right? What is the object that needs to be tested? What is the electrode system? Is it a set of 56 ground electrodes, or is it a single ground electrode? So understanding what it is that you're testing, how your test instrument operates, and then what your future uses may be, determine what it is that you need to do to apply to this test instrument, right? Lead length, it's a huge one. We were just talking about why remote Earth needs to be so far away. If you're testing something that's very large, it has a large horizontal component that has a ring of electrodes around it, or a grid of electrodes in the case of a substation, you're going to need to go much further to find that remote Earth. Because now I have more conductors in the ground, and they have a larger shell or set of shells, if you will, that I need to go further to find that remote Earth connection. So there's a lot that goes into this. It is a highly nuanced test setup that we can simplify for you if you'll just give us a call and give us the opportunity to do that for you.
Makes sense.
I'd like to add a few things on to what Gregg was saying. One is, if you are going to call, the manufacturers, absolutely, they can help you. Just make sure that you are a little bit specific on your test setup, right? So it's going to make a big difference whether or not you're doing online or offline testing, right?
Sure.
So, make sure that you identify those types of test characteristics when you're trying to have those conversations, especially when you're in a pickle or a pinch and you're like, I can't figure it out. Oh, well, and then it takes 45 minutes for the engineer on the phone to ask you the stupid question is, are you testing on a live grid? And then you're like, yeah. And you're like, you can't do any of this with that test. So have that conversation up front. Ask the stupid questions. I love the stupid questions because it's just low-hanging fruit. And so that's one thing. Another thing that Gregg was talking about, he was calling them shells. Quite often, when you read, it just depends on the literature that you're reading it from. Meggers, Getting Down to Earth, calls it spheres of influence. Mm-hmm. And so when he's talking about those spheres of influence, you're talking about, imagine that you have a ground rod and just put a 10-foot sphere in all directions around that rod. And every 10 foot it goes out, the resistance becomes much lower, right? Mm-hmm. That it's able to touch and conduct to Earth because you have more soil, more surface area on that sphere. So that's what he's talking about. And when you're talking about a really large ground grid, right? I've been out at some of these really large manufacturing plants, right? When they're building and they're literally just, they're digging Earth. And, they'll go out there and they'll start doing all their ground rods. You're talking about 2,000 foot in one direction by 3,000 foot in another direction, all interconnected ground grid the whole way through. And you're like, well, how do I test this thing as a grid? Mm-hmm. Well, these documents, IEEE, they're going to say 5 to 7, maybe even 10 times the diagonal length of the grid, right? Because you got to have this giant sphere. I can't just test a little bit of Earth right next to it. Right? You got to go 5 to 10 times out, so that way you can scale your meter properly. That's essentially what you're doing, right? Yeah, and so, if you end up doing that, I'm going to give you a cool tip right here. Is that I think IEEE 81 does a okay job of it, but Meggers Getting Down to Earth does a little bit better job of explaining the differences between some of the tests. Fall potential, if you're going to do a fall potential on that size grid, you're going to have to be like a mile out.
Yes.
Who's stretching test leads out that far? Like, get out of here, right? You're not doing that. That's just, it's going to take you half
not practical.
The set up,
yeah,
right?
It's not practical.
So, yeah, it's just not practical. So there are other tests that you can do. And one thing that I've done in the past that I highly recommend, and I mean, reach out if you're unsure. It's very difficult to crunch the numbers with, but if you make an Excel spreadsheet, it works perfect. Is called the intersecting curves method, and I freaking love this test. You can reduce the diagonal length that you have to test instead of 10 times. You can reduce it down to 3 shots now. You have to do 3 tests, but now it's 2 times, 4 times, and 6 times. Right? So it's much more manageable on larger grids. So that's a cool trick that you can do, but you have to seriously read the literature and perform those calculations right, or you're going to have wrong numbers every time.
To that point, real quick, before you move on, if we do work on the true spirit and language of what is in 81, if we read the follow potential paragraph, because it's just one paragraph in that document about follow potential, they do a good job of explaining it, but they leave a lot up for interpretation. Right behind that, though, is Tagg's slope method. And this is the method that I generally point people to because intersecting curves is very comprehensive. And it's a wonderful test procedure, and you're right, exactly right. You need a spreadsheet for this one. You're essentially performing multiple follow potential measurements. At the end of it, you should have somewhere between 30 and 40 or more measurements that were actually taken if you do it to the true definition of intersecting curves. And they're all follow potential like measurements. Slope is going to simplify this step even further. And we have a really, really great calculator that we developed on our website, as well as you will find all the instructions in IEEE 81 on how to perform slope. Slope is specifically purposely designed to test large, horizontally laid electrodes, like a substation ground grid, where I'm limited on space or for practicality. Here we're limited, or our distance is only 2 to 3 times the longest diagonal, and we're going to perform 3 measurements. Now they're somewhat arbitrary. We just need to establish a slope coefficient. Everybody remembers that from like pre-algebra or algebra 1. Rise over run, right? We're going to get a slope coefficient. We're going to check it in a chart, or we can use the calculator to do this as well too. The chart's going to give us a decimal multiplier for the distances that we've already established. So our H was out at, let's say 500 feet. It's going to say, go ahead and establish your S probe, your measurement probe at, let's say 71% of that distance to H. We're going to take another measurement. That's going to be representative of the resistance to ground of this electrode system. We'll repeat it. We'll do this multiple times, ideally not at 180 degrees. So we're not going to test to the south and then go test to the north. We're going to test to the south and then the southeast and then maybe the east or west or something like that as well too. And we should see numbers that are in agreement. I've seen this test procedure. I've not only mocked it up myself on just a small set of electrodes to compare it to follow potential. I've also seen it against follow potential in a very large scenario on a substation. The values are incredibly similar. And we know this because we have a ton of test data, not just me doing, it's an N of 1, a couple samples. I wouldn't rely just on that. We know that this is reliable because it produces reliable results, consistently throughout different types of measurements. It'll also error itself out essentially because the math won't work out. We will end up with, a negative value in many cases, where we're not far enough out there. So we're able to test inside those spheres, but to a limited degree. When we think about it from a or an electrical perspective, of the geometry. So definitely consider that test procedure.
Are you seeing that being employed more often in the field now, or is it something that's where did you find out about it? I guess would be because that's a new one to me on the text.
Yeah, so IEEE 81 specifically is where it not where it originates. GF Tag was a engineer and PhD professor in England, I believe, in the UK. He wrote the paper on the slope method in the 60s, if I recall correctly, and it has been repeated. The method is found in various documents throughout, though. Tend to get a lot of pushback on it. Tend to get well, I don't know if my customer will take that. And I think that's where, because it is in an IEEE standard, we have a little bit more ground to stand on.
Yep.
But I think, I'm sure Tom will agree with me, I think the best way to represent this, or any test procedure, no matter what it is repetitive values.
Yep.
Right?
Makes sense.
I do it, I get a value, I prove that value by repeating the measurement and constricting the variables, or the change in variables, to just one. Here, it is going to be the direction in which I test, but I could also constrict that change to distance.
Yep.
Right? So if I tested at 500 feet, maybe I can test at 600 feet, or I bring it into 420 feet, for instance. I wouldn't change two variables in that case. I wouldn't change direction and distance if I can control that. I would say another thing that's very true about ground resistance testing, unique. Every scenario is very different than the next, right?
That's true.
I don't always get the opportunity of having my ground system installed in a location where I have exactly the right distance to test for my H electrode to be placed out at 100 feet or whatever it may be. I'm going to run into scenarios where the test is going to be very different because of the spacing requirements.
Transmission line towers, all kinds of stuff.
Exactly, right? So it's not testing a breaker. Obviously you're going to run into some different variances location to location when you're doing breaker testing. However, it's a breaker. Right? There's only so many variables that can change versus a ground system, which I am very reliant on conditions in which I have no control over.
Yeah, and to Gregg's point, there are many other methods of calculating ground. What we're really talking about is our resistance to Earth with these methods, right?
Yep.
That's what we're trying to calculate. And so whether you're using follow potential, you're using intersecting curves, which is a bunch of follow potential tests that you plot over each other. That's all it is, right?
Right.
Or you're doing the slope method, the delta star method. There's a lot of different methods that are out there. What ultimately matters, and Gregg kind of alluded to this earlier, is IEEE is going to reference all this. It's going to give you the basic foundation for what you need to do. It's not going to hold your hand through it at all. You've got to do your research, right? But at the end of the day, it's the customer who's paying your bills. So if they don't accept that as a test method, good Lord, you better make sure of that one first. So that's one of my recommendations. Is have that conversation first with your customer. Hey, look, we can't do that follow potential at 3,000 feet. It's just not. I don't have the wire, and a lot of testing companies don't carry that in their back pocket. So we can alternate this test. Here's another one from IEEE. I mean, we are the SMEs. We're the subject matter experts, right? They come to us anyways. So if you go ahead and you give them this information, hopefully they're like, you know what, that sounds good. It's in IEEE. They'll run it by their engineer. He'll say, yeah, it's in IEEE. Of course it's okay, right? And then usually you're okay. You might have to explain yourself a little bit, so don't just totally let the IEEE carry you. You might actually have to know what you're talking about once in a while.
Believe it or not.
The other thing I'll say is, Gregg was saying this earlier about every site's different, right? Well, there's a couple things that we should also probably point out. Whenever you're doing resistance to earth testing or soil resistivity, both of those tests are highly influenced by weather and ground soil conditions. So you need to make sure that my recommendation is rain within the last week, but not within the last 3 days. That's how I typically like to do it, right? I don't want, and if you haven't had rain in the last week, okay, is that normal for your environment? If that's normal, then okay, right? But if that's not normal and you're like, no, it's been kind of a drought lately, although let's wait till it rains and 3 days later we'll go out and test it, right? Because you want to test something that's indicative of normal conditions, not an extreme dry or an extreme wet. And a lot of people are like, dude, it's a swamp out here. We need you to test it now. I'd be like, I'm going to give you perfect numbers. They're like, that's great. I was like, no, that's horrible. Like that is, if you just want me to check the block, I can do this from my house. I don't even have to.
Don't even have to go outside.
Okay, so no, let's go out there and actually do it right and give the engineer what he's really looking for, because they need these numbers when they're plotting like their step and touch potential into their systems to make sure that they can calculate fault currents right. They have to set their trip settings lower, so that they can lower the trip current, so that way they don't build up as much touch voltage when they're touching something. So they have reasons for these tests. So we need to make sure that we're doing it. The data to report is one thing that I had on my list, and that is crucial, right? What type of soil are you in? I had guys in the past, we go out there to a construction site. They had the grid here, a couple rods around it. We're testing it, shooting it all the way out. Well, they had to get the dump trucks through, so they made a gravel road right through here. And some of their probes went through the gravel road because they were doing every 10%, right? And so write that on the report. Don't be lazy. Write it on the report. I not trying to be rude to anyone, but it's honestly like it only takes a few words right on the report. 10 and 20% went through a gravel road. Resistance may not be truly accurate for what the ground would measure. And that's all you have to do. And then the customer will be like, what the heck is this? This would be like 3 months later. Engineers like, there's no gravel road out there. What happened? Well, we had them out there testing when there was a gravel road there. Right. So you just need to annotate your test conditions. What kind of soil are you in? What was your weather that day? Was it extremely dry? Yeah. All that stuff is critical. I mean, when we're testing a breaker, just to go on to that a little bit more, when you're testing a breaker, you're supposed to record ambient temperature and humidity, right? Right. You need all of that and more for ground testing, because what is the ground? It stays outside all the time, right? So you need the environment. Yeah, you need to record everything that matters for that.
Random one on that, Tom. So so we talked the gravel road being laid and then it not being there due to construction or whatever it may be. Is that gonna would that trigger like a new assessment basically at that point if you've changed something strategically within the Earth environment there, like a road or something like that?
Yeah. So the way that it's outlined in the literature, in almost any literature you read, is it's going to say you should be testing in a route that is not improved soil, right?
Native soil, yeah.
Gotcha. Yeah, so it's undisturbed, right? So if it's been disturbed soil and you're going up this bank and you're coming back down it, that bank is not going to be there in 3 weeks, right? They're going to come out and plow that thing out of there. So maybe you might want to test afterwards, right? And that way you're testing what the final product is like. That at that point, that is somewhat improved, right? But the thing is that the dirt under that's not improved, right? So if that dirt under that is disturbed and they ground it up and then they redid it and plowed it or whatever, then you might want to come back 2 weeks after that so it compacts back down into normal earth, and then and then reshoot your test. Yeah, because I've had people out there that they test and it's loose soil the whole way. Well, loose soil tests way worse than compacted soil. So, and it's drier usually too. It's drier and it's looser. So it's usually, it doesn't test as good. I mean, if you want good indicative numbers, test it the right way.
Yeah. And I think this is a really complex conversation and we cannot cover every nuance here. Yeah. Because this can get very hairy. There a few, but just a couple quick talking points on that, because I think this is highly critical. Be considerate of when your soil resistivity testing was done and then what changes were made to the site. Why do I say that? Because I've run into this many, many times now. We did a soil resistivity test on XYZ date and it was a green field, right? It was all native soil, and maybe it rained yesterday, whatever the rainfall conditions were. But we removed that native soil. We backfilled with a new material. And now our resistance is completely different than what was calculated, right? Very well-meaning engineers have made this mistake many, many times, right? It could be high voltage, it could be a substation, it could be a communication site, it could be whatever, right? We backfilled for structural reasons and we introduced, let's say, an aggregate, and that aggregate brings in, especially when freshly laid, and freshly here could be up to, maybe a year or more, it's going to be porous. The soil is very porous. It has an air gap, and we use air as an insulator all the time. It's not great for making that connection to the rest of the earth that's
Yep.
around it. So we want to be considerate of that. Next thing is, and I'll end it here, is going to be the test instrument, right? An instrument of this caliper, like this 6472, I get probe resistances with this, right? I get errors that will be produced. I'll get a greater than, a less than symbol. Sometimes I can even produce both. And what that's telling me is, yes, I produced a value. Yes, there's a value being displayed here. However, it doesn't meet the specification for accuracy. What
Yeah.
is the instrument doing? It's sampling, right? There's an AC test current flowing between those 2 points, pushing and pulling. It's taking samples of that measurement as that test current is being transmitted through the earth. By doing that, I can then compare those samples and say, hey, this is a problem because my sampling is very different. The deviation between these measurements is too great to call this accurate. So when we can get this, especially in high resistance soils, where, like Tom mentioned, there was a gravel road that was laid, or I disturbed the soil at this site to accomplish whatever, usually some type of structural change or structural addition that needs to be made to support whatever is being constructed. We put our ground electrodes in that disturbed soil, and my probes then, which are electrodes, are placed in the earth in also disturbed soil. Now they have a high resistance. Benefit to fault potential and fault potential variance like slope and intersecting curves. The probe resistance can be an order of magnitude substantially higher in resistance than the electrode that is under test, but there is a threshold there. It can't be a 5 ohm system in a 10,000 ohm probe. We're not going to get a good test setup. Buy an instrument. If you're doing these types of measurements pretty consistently, buy an instrument that gives you those values, because now I can troubleshoot what the problem is with the measurement. Maybe I'm testing to the northwest, and the northwest is in a direction in which an aggregate plant is, right? And they have a lot of waste that's poured over. Or a recent experience I had, there's a trash dump this direction, and they laid a membrane down, right? Now they've abandoned it since. It's no longer in operation, but that membrane is causing me to have very, very high resistance soil, and I'm not able to perform my test. Now I'm going to test this way. What else is going to be valuable there is I need to put that on the report. My test probes were laid out this direction. I like the idea of giving a test report that not only gives me all the values and the conditions, but it's just a simple map that of the direction in which I tested, where I made the connection to the electrode system, and so on and so forth. The more data, the better there. It's a CYA thing there. Tom mentioned rainfall, right? I like your idea of waiting to make sure that we're in that Goldilocks zone of it rained, but not too recently and not too long ago. Notate the last rainfall. Google is your best friend on some type of data point like that, right? Also consider how much rain fell. If I'm forced to do a test today and it rained yesterday, but what does that mean? Did it sprinkle yesterday, or did it pour rain for 6 hours? So we want to be considerate of everything that can have an effect on a resistance measurement that is introduced into the soil and around those electrodes. Overall, we observe frost lines for that for many reasons, but that could be one of those reasons. We go from 32 degrees water to 32 degrees solid frozen ice. We see a resistance change that could be 3 times what the resistance is at 32 degrees liquid. So we can see all sorts of things that'll change there. That's why I like the inter-season testing perspective, because I build a profile, right? I'm going to give you the last thing, and I harp on this big time in seminars and to anyone that I talk to about this subject. But let's be ethical in how we do our tests. What do I mean by that? Now, in your scenario with NIDA testing, you're giving these results into a customer. This may apply to maybe an alternative test. Maybe I'm doing a test for someone that doesn't have a great understanding of what these values are. Or it's a CYA thing on my part. My threshold for what's good, what's bad is 5 ohms. Let's say I go and I do a test and it's 4.8 ohms. Let's be considerate of accuracy, right? Not so great in ground resistance testing. I repeat the measurement, whether it's taking multiple fault potential measurements on my traverse to H, or I turn that test and do another fault potential measurement, and I get values that are very similar. Let's say it's 4.8 ohms, my threshold's 5 ohms, right? I'm going to put an asterisk on that. I want to be considerate of all those all those conditions that I'm in. Maybe it's April and it's unseasonably wet. What's the resistance going to be in July when it's unseasonably dry? So we want to be considerate of the value and making sure that there's headroom on that value given the environment, given the scenario. So be aware that just because you have a threshold and you've met it doesn't mean that it should necessarily pass in that particular case, right? And that can be applied to any type of electrical testing or anything in life, of course. But, the same could be true with insulation testing as well, or low resistance testing.
I want to say two things real quick. One is going to be...
We're going to just keep doing this.
Keep it going, baby. Keep it going.
Where a lot of people are like, what should my number be? Right? When you're doing resistance testing.
Get it.
Yeah. And I'm going to give you the quick, dirty three answers. Okay. So depending on whether you're looking at the NEC or the NESC or the IEEE, right? It depends. So a normal residential is going to be 25 ohms or less. Okay. So that's typical normal. I see your shrug. Normal, typical residential, maybe even commercial. Okay. Industrial is going to be anywhere from 25 ohms or less to 5 ohms or less. And then when you start talking about substation, even some distribution substations might be 5 ohms or less, right? Mm-hmm. But if you're talking about transmission or generation, then we're talking about the big boys here. Those are going to be 1 ohm or less almost every single time. So depending on your specific requirement and what your engineer also requires, but you're getting paid by them, right? So that's ultimately what matters. But where do they pull these numbers from? That's where they get them from. So those are usually the three general numbers that you might see. And I've seen some customers say they need to be 8 ohms or less. I was like, I don't know where you get that number from, but fine. We'll roll with that. But I just want you to know that that's where they come from, the IEEE, the NESC, and the NEC. All three of those are generally the three major ones. That was the first thing. The other thing I wanted to point out was I want to use two scenarios, right? I had a customer, I didn't have a customer, but there's a customer in the past I was working with, and they had a solar field, and a really big solar field, and they had lots of inverters out on strings. And you got to think these solar fields are huge, right? They're big sites. And so each one of those systems is it's a grounded frame essentially, and it's got grounding wire running under it. And they're like, this is already built. We want to test the grid resistance. I'm like, how the hell do you want to do that? So they wanted to go ahead and they wanted to get there are some proprietary special meters out there that you can get, like Duval, Hood, Patterson, and Duval, I believe is one of them. And they have some specialty meters out there. Are they good? As far as I know, yes. The guy that did that, that created that company, also co-founded and wrote IEEE 81 with the original author, I believe. So are they great meters? Yes, but I'm going to caveat that with yes, but those types of meters require very specialized software and training in order to perform the assessments properly. So if you're going to do that, make sure that you do your research. The other scenario I'm going to lean on is know your system. What is the intent of grounding? Like we said earlier, right? You've got your resistance to earth and then the integrity of your grid. That's really the two things that you have. And know what test you're testing and which one of those you're testing. So we had a customer here locally. They're like, hey, we're downtown. We need to test our ground grid. I was like, okay, well, what are you trying to do? We're trying to check resistance to earth. I was like, dude, you got gas lines, water pipes, everything. You got a customer 10 feet next door. There's no way you're going to get this. He's like, well, how do I know what my ground resistance is? I was like, just go from your main panel to the utility pole. And if you've got 0 ohms with a point-to-point check or 1 ohm or less, then you essentially are on an infinite grid. There's no check that you can do. Right? So know your limitations, understand the intent of the test. And at that point, he was like, look, I'm trying to check something that I already know is perfect. So at that point, you're not going to have step and touch potential in the backyard. It's not possible because you're on the infinite grid with water pipes all around you. So just understand the concepts of what you are testing and how to apply those tests.
Yep. 20, awesome. 20.
Any more last minute, by the way, is here. We got a little bit of time here.
I got to make the argument here just because I've spent some time on this one because I've been asked this question a lot is, what is 25 ohms? Why is 25 ohms the value? And it is an illusion to 25 ohms if a single electrode is driven. So that's NEC 250.52, if I recall correctly, 52 or 54. I'm not Mike Holt, as you can tell. So single ground electrode, 25 ohms or less. Two ground electrodes installed at least 6 feet apart, which we know that, and the NEC acknowledges this, the paralleling efficiency of electrodes can be greater if we put more space in between those electrodes, but they say 6 ohm or 6 foot minimum spacing between those electrodes. The number, it does not state that we need to retest. So 25 ohms or less on a single electrode, or just install 2 electrodes. What do we see for general purpose grounding? We see 2 electrodes installed, right? Now the NESC, as you mentioned, does have a specification in there, but it is somewhat similar. So we know that 25 ohms and the origin of 25 ohms, and I'm not going to be exactly correct on this because I don't know that this is exactly the right answer. However, it's from telegraph. So we're talking about something, and there's a coincidence there that with telegraphs, we knew that if we could get to, I believe it was a 50 ohm resistance, but we were in series with each other. So we were doing just a, referred to as a dead earth test, where we are essentially doing continuity through the soil. We would eliminate or minimize common mode voltages. We wouldn't have noise on the line. So we're talking about something that's very, very old there, in its reference. I know from traveling all around the country and the world now, doing soil resistivity and fault potential measurements in, like, for instance, the Pacific Northwest, especially as you get closer to the coast, 25 ohms is an illusion to think that you're going to get that with 2 electrodes. It's just not going to happen in most of those locations because they're either heavily rocky or they have very poor soil, or both in many cases. So it's very dependent on where you're at and what you're going to produce value to value, but be aware that 25 ohms is kind of just a made up value. I'll add to Tom's comments though about what's a good and a bad value. I never like to engage in this conversation because we're on the testing side of things. I can tell you what it is and how I can guarantee you that this value is accurate. But Tom mentioned earlier, we're going to be considerate of the environment. This is an apparent measurement. And I think that's important to nail down. It's apparent because it's today at 3 p.m. Today at 6 p.m. it rained. So now the value is going to be different, right? Or in 6 months it was drier, or whatever the case may be, right? The soil gets disturbed, whatever. We've mentioned all these different variables that can affect it. So we want to be conscientious that this is an apparent value and it's going to change. And that's true with most of the testing that is going to be done by the group of viewers that would take a look at this. But it's going to be more extreme with ground resistance measurements. Gotcha. They're going to change quite a bit. So, just be aware that these values and how they're laid out or what their specifications are can be, they can come from all over the place. IEEE 142 is going to say 5 ohms or less. Like they're just going to say 5 ohms or less, period. And they may specify even lower than that. Specifications, though, from manufacturers are really what drive a lot of very low resistances. So Motorola, for instance, like we mentioned earlier, is going to classify different sites for what their intended purposes, class B, class A, so on and so forth, have to have different resistances because they are either critical or less critical or non-critical in that case. Lightning protection systems can have different values depending on where they're located. We're looking at what kind of system was installed, what the flash density is of that location, and does it need to have a 1 ohm or a 5 ohm or a 25 ohm resistance value, oftentimes specified as being 5 ohms or less. So these values here, I never like to engage in this argument. What's better? Lower, period. Always. It's a golf game. If you get to 5 ohms with a single electrode, great. You have a 5 ohm resistance connection to the earth. I think it's important too that we nail this one down as well. We don't just install ground electrodes to get to a low resistance connection. Tom kind of alluded to this earlier. Just because I have 5 ohms on one over here in let's say the northeast corner, doesn't mean that I don't need more electrodes, because I'm also controlling voltages in the earth. Right. So I have those shells that we described earlier. I like zones better, that tell me that if I can have these potentials that are created on, different ends of my installation or whatever the case may be. So we don't just ground just specifically to we just don't ground just specifically to limit voltage in one location to have a 5 ohm resistance to earth. We need that system to be, to control the earth voltages to minimize those, gradients that are created when we do have a fault condition, overall. So, there's again a lot of nuance here on the values. I think that for this topic of conversation, let's leave that to the guys writing the specification, the standards, whatever it may be. That's what's critical. How we produce the value, how we know that the value is accurate, and what the extenuating circumstances of those values are critical for this conversation. Rainfall, what the soil type is. I'll mention a quick trick on that. The USGS maintains a ton of data on that, and it's all free. There's a map that you can get on their website, and you can pinpoint the location that you were testing at to see what the soil constituents are. That's not going to be an exact example, but it's good enough in most cases to notate what kind of soil you were testing in. You mentioned temperature and all that kind of stuff. I think rainfall is the most critical one that we can notate there. But the direction in which we set out our test probes, because that's one of those variables that I can constrain. I can control that for future testing. If I tested in the northeast corner this time, I'm going to perform the test again in the northeast corner. Was the system isolated or not? Sometimes we see this testing prescribed on systems that are not isolated. This shows up in a lot of lightning protection systems. They're not going to de-energize. They're not going to isolate the system because it's either impractical or impossible to do so. They're going to repeat the test the same exact way over and over again. Is that truly the resistance to ground? Absolutely not. But by repeating the test over and over again, we can at least establish some repetitive values that we can trend over time. So, understanding why the test is being done and the spirit of which the test is being done is, I think, critical as well too. So, a lot of stuff we covered there.
That was a lot. It was very, very good and very in depth, and I definitely feel a bit smarter on that. Now, for anybody that wants to reach out, obviously, Greg, you're a major part of this function. What's the best way for people to connect with you?
You can always send me an email at gwong@aemc.com. Or reach out to AEMC. I will also mention too, our tech support is US based. They actually answer the phone. Like, believe it or not, that's a wonderful,
it is huge,
novel function, right? Now we have 2 tech support agents, that are answering the phone 8 to 5 Eastern time. If they don't, for some reason, answer the phone, they're probably busy with another customer. They'll call you back, right? You can send us an email. What I love about our email addresses is they're super easy. It's techsupport@aemc.com. If you want to get a hold of any department, you can just usually type in the name of the department, aemc.com. So reach out to us, though, even if it's not our instrument or you're in the buying mode or you need to know what instrument to purchase here, or you're in the design mode of your system and you want to know what the best interval for testing is. We're happy to assist there as much as we can where we know we can. So we have some very knowledgeable people on the phone that'll definitely help.
Awesome. And Tom, same question to you, man. Where can we find you?
So probably the best thing is just to reach out to me on LinkedIn. I like to stay I usually stay pretty active on there. If you got the time to check it out, check out the YouTube Testing with Tom. I got some stuff on there. All my LinkedIn videos go over to YouTube. So not the pictures in the post, but at least all the videos. So if it interests you, I appreciate you checking it out. Hopefully,
great content, and I love watching it. So it's been very good.
When are you going to make like a Patreon so you can start making some cash?
Right, make some money off this.
Yeah,
I'm not doing it to make money, man. I'm doing it.
I know, yeah, but it's really good content. Like your transformer.
Very good.
Setup was very
with the bus
impressive.
bars. When had all the bus bar breakdowns and stuff. It was fantastic.
Do you like that little bus bar thing I made?
Yeah, I'm doing watching it, then. See.
Yeah,
that's pretty cool.
Fantastic.
Yeah,
spent more time making that damn thing than I did making the video.
Yeah, the transformer setup that you built was pretty impressive.
Awesome.
Too, so I enjoyed that
much.
As well. Yeah.
So probably going to do more with that too.
Yeah.
I love it. Well, gentlemen, as always, thank you once again for making an appearance over here, and we'll have some graphics and some references in there that we'll get on the backside of it and plugged in. And just truly appreciate it as always what you guys do as a force for good. I'm looking forward to hopefully seeing you both at Power Test. I know Tom said he's going to be there. Greg, you going to be there this year?
Absolutely.
All right. Well, then we'll have to break bread once again and do it again.
Yeah.
And probably not going to do it live from there this year, maybe next year. So,
yeah.
But we'll get her done, and it'll be a blast. But gentlemen, thank you so much once again for hopping on and educating. It was truly awesome, and covering everything that comes to do. Well, not everything, right? Because it's such a vast
big topic.
Subject. But we did a great overview, or you guys did. I just asked silly questions along the way and nod a lot. So mission accomplished on my end.
Yeah.
But truly appreciate it as always, guys. I think there's going to be a tons of value add coming out of this thing. So thanks again once again for joining us. And as always, if you want to hop on at any given time, there's an open invitation. And with that being said, until next time, folks, Mike out.